Now let's take a look at the delocalization of lone pairs and carbanions. Just in terms of terminology, remember that a lone pair is an atom with 2 electrons on it like that. A carbanion is a carbon with a negative charge. But when you have a carbanion, that carbon will have a lone pair on it. So carbanions fall into the category of carbons with a lone pair. Let's start with a simple structure and look at a propyl anion. And I'm going to use this carbon in the center, and typically this carbon would have 2 hydrogen on it, but if it has a lone pair and a negative charge, that takes the place of one of the hydrogen. So I'll draw 1 hydrogen in just to specify that there's 1 there, and then I'm going to put a lone pair on that carbon. And that carbon will now have a negative formal charge. Right, in terms of the hybridization of this carbon, let's look at that. This carbon has 4 groups around it. 3 groups are the bonds. 1 group is the lone pair. All right, don't count the negative, that's just a formal charge. So if you have 4 groups around an atom, that is sp3 hybridized. Let's review the hybridization schemes for carbons at various hybridizations. What you always start with on the carbon are 4 orbitals, an s orbital, and 3 p orbitals. And when those orbitals go into hybridization, you always get a total of 4 orbitals out. So 4 in, 4 out. Right? If all 4 of these mix together, what you get is sp3. 4 in, you get 4 sp3 orbitals out. Okay, now if one carbon has a p orbital that's reserved, and you mix the s and 2 p orbitals, so you mix these 3, you get 3 sp2s out. So in an sp2 scheme, you get 3 sp2 orbitals plus the 1 p orbital that didn't go into hybridization. Right, finally, the sp scheme. In sp hybridization, 2 p orbitals are reserved and they don't go into hybridization, but the s and 1 p orbital mix. So s and p mix together to give sp, but since there's 2 going in, 2 come out. So we get 2 sps plus 2p. So now, coming back to our carbanion, if that carbon is sp3 hybridized, that means that the lone pair must be in an sp3 orbital, because that's all that carbon has. The orbitals on this carbon, 4 sp3s. 1 is used for this sigma bond, 1 is used for this sigma bond, 1 is used for the CH sigma bond, and number 4 is where the lone pair resides. You should be able to look at this structure here and know that there's no resonance structures you can draw, But a way to confirm this is the fact that the lone pair in the sp3 orbital, it's not going to be delocalized because you need p orbitals for delocalization. Let's look at another example. Here we have an allylic carbanion. So this is the carbanion counterpart to the allylic carbocation. Just to make things a little bit more clear, I hope, I'm going to draw in all of the hydrogen, which isn't something you have to do, but I think it'll help in clarity. Okay, and what I want to focus on is the carbon that bears the negative charge, or the lone pair here. If you look at this, and you do just like we did above, and count the groups, we have 3 sigma bonds and a lone pair, 4 groups that appears to be sp3 hybridized. And remember, hybridization refers to the atom, so the carbon atom. So you can write C. All right, but you know a thing or two about resonance, and we can draw a second resonance structure for this. And I can take this lone pair, push it here to form a pi bond, and that will push this pi bond onto the carbon as a lone pair. Let's draw the resulting structure. Here we now have the pi bond on the right side and the lone pair and negative charge on the leftmost carbon. Again, let's still look at the same carbon right here in red. Now if I ask you to look at the hybridization and count up the groups, we have a single bond, and a double bond. And the double bond counts as just one group. So 3 groups. This now appears to be sp2 hybridized. So we have a conflict between the 2 resonance structures. But the carbon can't be one and then the other, because we just have a single hybrid structure that must have a single hybridization at each atom. So what is real? Well, in this case, it's actually sp2 hybridized. Okay, now there's kind of a quick trick you can use for this. Draw all resonance structures, look at the hybridization, and the one that has more S character is the one that will be correct. But we don't want to just memorize that. So let's think about why this carbon is actually sp2 hybridized. Well, in reality, this lone pair is not in an sp3 orbital. It's in a p orbital so that it can delocalize. Remember, you need a p orbital in the atom for delocalization and resonance. So if I draw the sigma framework for this, and we draw p orbitals where the double bond's at, if we want this lone pair to delocalize, we need a p orbital on this leftmost carbon. And here's where the lone pair can be. Well, if that carbon has a p orbital, it can't be sp3. Look up here. sp3, all you have to work with are 4 sp3 orbitals. Since we have a p orbital on the carbon must be sp2 hybridized. And because we've put that lone pair in the p orbital, we have delocalization and a conjugated system. Let's look at just a couple other examples. Here you have an amide, and on first glance, if you look at this nitrogen, you would count 4 groups. 2 N-carbon single bonds, an NH single bond, and the lone pair. So again, that looks sp3. But if you draw the resonance structure, we get this. And now, if you look at how many groups are on the nitrogen, we just have 3 bonds. Remember, you don't count the positive charge as any type of group. So the 3 bonds around that nitrogen, it's sp2 hybridized, and that is the correct hybridization for the nitrogen. We can draw a p-orbital picture for this. Remember, we'll start with our sigma bond framework, where you have the carbon and the oxygen. There's a double bond, so we'll put a p-orbital on each of those atoms. And then the nitrogen, because it's sp2, it will also have a p-orbital. And that's where the nitrogen lone pair resides, at least if you're thinking about this original resonance structure. It's often hard to see in these drawings, but it is important to note that for delocalization, the p-orbitals must be in parallel alignment. Something we'll talk about later on is what happens if a forced bond rotation occurs that moves a p-orbital out of parallel alignment. If that happens, that will break the conjugation. Here's one other example where we have this enolate structure with a negative charge on the oxygen. We can draw resonance structures for this. So I can push, I'm going to use the negative charge as kind of a lone pair surrogate here. Push a lone pair down to form a double bond, and that'll push this negative charge onto the carbon. And then we can draw another resonance structure, push this to here, and push the pi bond onto the carbon. Okay, so with this series of atoms, at some point, they're all part of a double bond. Double bond, double bond, and even this carbon that has the negative charge in one resonance structure, it has a double bond. So if you were to go through and look at these, you could classify every one of these carbons as sp2 hybridized. Every one of these carbons has a p orbital, and this is a delocalized system. In fact, we have 1, 2, 3, 4, 5 atoms in conjugation. It's worth mentioning that part of a molecule can be in conjugation while another part may not. So here, these 5 atoms are part of the conjugated system, the delocalized system. These 2 atoms are not part of conjugation.